Imagine you're standing on a massive reinforced concrete pier. You're looking out at a transport vessel that is roughly the size of a naval aircraft carrier.
Right, they're absolutely massive.
Yeah, and inside the belly of that ship sits a payload cooled to an astonishing minus 160 degrees Celsius. I mean, to put that into perspective for you, this is a temperature so aggressively extreme that, well, if you were to submerge a standard rubber ball into this liquid and drop it on the deck,
It wouldn't just bounce.
exactly, it would instantly shatter into 1,000 pieces, exactly like glass. So this is liquefied natural gas, or LNG. Today, our deep dive is investigating the highly sophisticated, really high-stakes feats of cryogenic engineering that secure this volatile lifeblood of our global energy infrastructure.
And it is a phenomenal logistical and, frankly, scientific challenge.
It really is. We've synthesized an extensive body of technical blueprints, engineering manuals, incident reports, you name it. And our mission today is to decode how we actually managed to keep this highly reactive substance from boiling away, or worse, structurally compromising the very earth it sits upon.
Right, because what we're really investigating here is the precise art of managing transitions.
Yeah.
I mean, cryogenic engineering is fundamentally about maintaining a highly volatile substance in a fragile state of thermodynamic equilibrium.
Thermodynamic equilibrium.
Yes, you're attempting to completely isolate this exceptionally dense ultra-cold liquid from the massive temperature differentials of the outside world. It's a perpetual state of controlled resistance against the natural laws of thermodynamics.
Which is fascinating. And before we can understand how these facilities operate dynamically, we really have to look at their structural anatomy, right?
Absolutely.
When you see a modern LNG terminal, the most dominant features are these imposing cylindrical above-ground tanks. I mean, they look like absolute fortresses sitting on the coastline.
They do. They really are fortresses.
Our sources describe these as the full containment gold standard. So let's unpack the architecture of these fortresses, because the dual barrier system they employ isn't just about throwing thick metal at the problem.
Far from it. You have to assume from a strict engineering standpoint that the primary containment vessel might fail.
Right.
Therefore, the inner tank is forged from 9% nickel steel. And this isn't your standard industrial metal.
Because standard steel would just freeze. Right?
Exactly. At minus 160 degrees, standard carbon steel experiences a total loss of molecular mobility. It becomes horrifyingly brittle. I mean, a minor impact would crack it wide open.
So how does adding nickel solve that? Does it just make the metal harder?
It makes it more flexible. The introduction of 9% nickel structurally alters the crystal lattice of the seal.
Okay.
It acts almost like microscopic shock absorbers within the molecular grid. This specialized alloys is deliberately chosen for its ability to maintain exceptional ductility.
Ductility meaning it can bend.
Right, meaning it can still bend, flex, and absorb stress even at those bone-chilling cryogenic temperatures.
Okay, so we have this incredibly resilient, specialized nickel inner tank. But, looking at the blueprints provided in our sources, there's also a massive outer shell constructed of post-stressed concrete.
Yes, the secondary barrier.
Right. But if that primary container is already built from an advanced alloy that's specifically designed to withstand extreme thermal stress, isn't a monolithic concrete shell, structurally redundant? It feels like an exorbitant over-engineering of the perimeter.
Well, the redundancy is intentional, and it's entirely necessary to prevent catastrophic failure. To understand why, you really have to look at the disastrous consequences associated with older single containment models.
The legacy systems.
Exactly. In those older systems, if the primary tank suffered a breach, the liquid would leak into a simple open-air dike or bund wall.
Oh, I see where this is going.
Yeah, the immediate consequence of minus 160-degree liquid hitting ambient air is explosive evaporation. You don't just get a puddle.
Right, it boils instantly.
You get a massive, drifting, ground-hugging cloud of highly combustible vapor just seeking an ignition source.
Wow. That's a terrifying visual. A literal fog of explosive gas rolling across a coastline.
Which is exactly why the modern full containment outer concrete shell is specifically engineered to accomplish two critical imperatives. First, it must hold the entire volumetric capacity of the liquid in the event of an inner breach.
Okay, so it physically holds the space.
Right. And second, crucially, it must hermetically seal that vapor inside. And this isn't just poured concrete. You mentioned post-stressed concrete earlier.
Right, yeah. The sources emphasize that term heavily. What does post-stressing actually do in this context?
Well, think of a row of books on a shelf. If you try to pick them all up by pressing just the ends together, the ones in the middle will slip and fall.
Sure.
But if you apply immense inward pressure, squeezing them tightly, they act as a solid unified beam.
Oh, wow. Okay.
So post-stressed concrete contains thick steel cables threaded right through it. Once the concrete cures, hydraulic jacks pull those cables incredibly tight, permanently compressing the concrete inward.
So it's always under tension.
Exactly. This counteracts the immense outward pressure that a liquid spill would exert, while simultaneously protecting the volatile internal cargo from external threats.
External threats like adjacent industrial fires or direct physical impacts.
Precisely.
So it's not just about keeping the liquid in, it's about completely isolating the physical state of the gas from the atmosphere.
Exactly right.
But, you know, what happens when the geographical environment itself is a direct threat to these concrete fortresses? I mean, you can build the strongest post-stressed shell in the world, but if the ground beneath it violently ruptures, that structural integrity is severely compromised.
That is a major engineering hurdle.
Right, and our sources detail this fascinating countermeasure for seismically volatile regions known as the Japanese in-ground storage strategy.
Yeah, in geographic zones where seismic activity is a continuous high probability threat, building a towering above ground monolith introduces severe vulnerability.
You're just asking for trouble.
Pretty much. So the in-ground strategy fundamentally alters the physical relationship between the storage vessel and the Earth. Instead of fighting the seismic waves, you engineer the tank to move harmoniously with them.
It's a brilliant pivot in engineering philosophy. If you picture an above-ground tank during a severe earthquake, it's essentially acting like a heavy, rigid pendulum just waiting to snap at its base.
That's a great analogy.
Right. But contrasting that with the in-ground approach, you're looking at a structure that uses the earth itself for stability. It's essentially a bunker.
A very sophisticated bunker, yes.
But digging a massive pit and dropping a tank into it, well, that can't be that simple. The earth is heavy and full of groundwater.
It is an incredibly hostile environment to build in. The sources highlight a critical mechanism utilized in these excavations, the slurry wall.
The slurry wall.
Yes. Before you even dig the main pit, engineers trench a massive deep ring around the perimeter and fill it with a dense liquid slurry. As they excavate the earth from the center, they gradually replace the slurry with reinforced concrete.
So what is the mechanical purpose of doing it that way? I mean, why not just dig a big hole and line it later?
Because of hydrostatic pressure. The surrounding soil is deeply saturated with groundwater. If you just dug a massive empty hole, the sheer outward pressure of the surrounding water and earth would collapse the walls inward instantly.
Just crush it like a soda can.
Exactly. So the slurry, and eventually the concrete, provides immediate structural pushback. It maintains the integrity of the pit while they work.
That makes total sense.
And then, inside that concrete casing, engineers install rigid polyurethane foam insulation and a stainless steel membrane, and then cap it with a dome-shaped carbon steel roof. It's a massive capital-intensive engineering undertaking.
I can imagine.
But the unparalleled seismic resilience it offers makes it really the only responsible choice for high-risk tectonic zones.
So the environment dictates the architecture just as much as the cryogenic liquid itself does.
Absolutely.
But let's look at another alternative our sources highlight for above-ground storage, the membrane tank. If the full containment design we talked about earlier is a heavy fortress, the membrane tank is presented as this elegant, lightweight alternative.
It's a very clever design.
Because the inner tank isn't thick nickel steel at all, right? It's a corrugated, flexible stainless steel liner.
Right. The membrane tank represents a sophisticated shift in how we manage load distribution. In a traditional inner tank, that thick steel wall must possess the structural integrity to bear the immense hydrostatic load.
So the weight of the liquid.
Yes, we're talking about the sheer crushing weight of hundreds of thousands of tons of liquid pressing outward against the metal. The membrane tank circumvents this entirely.
But how? How does a thin liner hold back the weight of essentially a skyscraper made of liquid?
Well, it doesn't.
It doesn't.
No, the internal stainless steel liner is remarkably thin, often just a little over a millimeter.
No, millimeter, wow.
Yeah. It's corrugated, meaning it has these folds that allow it to expand and contract like an accordion. So rather than the metal bearing the hydrostatic load, the load passes right through it.
Through the metal.
Exactly. The pressure is transferred directly through a dense layer of specialized load-bearing insulation outward into the post-stressed concrete wall.
Oh, I see. So the concrete is doing all the heavy lifting.
Precisely.
The flexible steel liner simply acts as a waterproof, or I guess liquid-proof skin. It's like lining a concrete swimming pool with a plastic tarp.
That's a perfect way to visualize it.
The plastic isn't holding the water pressure the concrete walls of the pool are. The tarp just stops it from leaking out.
Exactly. It maximizes space efficiency and drastically reduces the amount of specialized steel required. But of course, it demands a profound understanding of how materials transmit force when subjected to minus 160 degrees.
Which brings us to the next point perfectly. Because having established how these formidable structures withstand both internal pressure and external seismic forces, our investigation really has to turn to the hidden microscopic wars being waged constantly within these facilities.
The thermal battle.
Right, the battle against thermal expansion and contraction. And here is where the engineering becomes, frankly, beautifully counterintuitive.
It really does.
Imagine authorizing the construction of a multi-billion-dollar facility designed exclusively to keep a liquid payload isolated at minus 160 degrees Celsius, and then intentionally installing a network of active heaters directly beneath it.
I mean, to a layperson, it sounds like a critical design flaw just waiting to happen.
It really does. Wait, you're telling me we spend billions to freeze this volatile substance and then we put electrical cables or warm glycol pipes right under it?
Yes.
How does that not just violently boil the entire tank from the bottom up?
Well, if we analyze the thermodynamic reality of the site over years of operation, we encounter a slow-moving geological disaster known as frost heave.
Frost heave.
Okay. Despite the implementation of state-of-the-art base insulation, a slow, relentless migration of extreme cold into the subterranean soil is, unfortunately, inevitable.
The cold just leaks out over time.
Exactly. And without intervention, that freezing front pushes deeper and deeper into the bedrock.
And the ground freezes. But, I mean, it's just dirt. Why does frozen dirt matter to a massive concrete fortress?
Because of the moisture trapped within that soil. As water freezes, it crystallizes and expands.
Oh, of course.
Now imagine thousands of cubic meters of subterranean soil expanding beneath a heavy, rigid concrete foundation. And it doesn't expand evenly.
It pushes up?
Violently. This expansion would exert massive, uneven, and ultimately catastrophic structural upward stresses onto the base of the tank. It would literally crack the foundation in half.
So the bottom heaters aren't there to warm the tank itself, they're acting as a thermodynamic shield.
Exactly. They intercept that migrating cold front before it hits the groundwater. They maintain a localized zone of thermodynamic equilibrium. They create a soft thermal cushion within the soil, actively defending the foundation from the destructive forces of frost heave.
You are essentially manipulating the geology beneath the facility to accommodate the physics of the tank.
That's exactly what you're doing.
That is incredible. And that brings us to another physical transformation detail in our research, which is frankly hard to visualize until you hear the number.
That is shrinkage.
Right. An 80-meter wide steel tank doesn't just sit there static when filled with LNG. The extreme drop in temperature causes the massive metal structure to physically shrink by several centimeters.
Yes, the metal contracts significantly.
And if you don't engineer flexibility into the void between the inner steel tank and the outer concrete wall, the sheer force of that contraction will tear the facility apart.
The insulation strategy here has to be highly specific. You can't just leave that 1 to 2 meter gap between the inner and outer walls empty.
Because it would just be a pocket of air.
Right, and you also can't fill it with something rigid. So in many designs, this buffer zone is filled with perlite,
which our sources describe as expanded, lightweight, volcanic glass bubble.
Yes, perlite provides phenomenal thermal insulation, but mechanically, it behaves almost like a fluid. It's a loose film material.
And the sources highlight a major hazard here. If you just poured loose perlite into that gap, the physical movement of the inner tank shrinking and expanding over years of operation, well, it would cause those glass bubbles to settle.
That's the compaction hazard.
They would gradually pack down deeper into the void, and eventually they become so densely compacted that they would act like a solid wedge.
Precisely.
So when the inner tank attempted to expand again, that solid wall of perlite would just crush the very tank it was meant to insulate.
It would be disastrous.
Yeah.
So to counteract this, engineers employ a highly effective, seemingly low-tech mitigation protocol.
I love this part.
They wrap the entire exterior surface of the inner steel tank in thick fiberglass blankets.
It's just so simple. It's like wearing a puffy down winter coat underneath a tightly pulled seatbelt.
That is a great visual.
If you shift your weight, You need that squishy, resilient layer so you can still breathe and move against the tension.
That's the exact mechanical principle at play here. As the massive steel inner tank expands and contracts with thermal cycles, the resilient fiberglass layer compresses and rebounds.
It takes the hit.
Right, the springy cushion absorbs the movement, preventing the perlite from settling into a dense mass. It ensures that the contracting metal structure always has the necessary breathing room.
It's just fascinating to realize that within this fortress of post-stressed concrete and specialized nickel alloys, the catastrophic failure of the entire system is basically prevented by the simple, squishy resilience of a fiberglass blanket.
Engineering is often about elegant solutions to brutal forces.
Absolutely. But we have to transition our deep dive from these passive structural defenses to the active mechanical heartbeat of the terminal. Because as our sources make abundantly clear, an LNG tank is not a static storage box.
Not at all.
It is a breathing, highly dynamic pressure vessel.
Right, because no matter how sophisticated your perlite and fiberglass thermal cushions are, heat ingress is a thermodynamic inevitability.
You can't stop it entirely.
You can't. And this invisible intrusion leads to what the industry calls boil-off gas, or BOG.
BOG.
Yes, even under optimal operating conditions, approximately 0.05% of the liquid volume evaporates into gas every single day.
Which honestly sounds statistically insignificant until you calculate that percentage against a tank the size of a football stadium.
It's a massive amount of gas.
That tiny fraction equates to thousands of kilograms of violently expanding gas, generating tremendous pressure every single hour.
Yes.
And venting this gas into the atmosphere is obviously a severe environmental violation and a massive economic loss. So how does the facility handle a continuously expanding cloud of internal pressure?
Well, the terminal acts almost like a massive respiratory system. It utilizes high-capacity compressors to capture that vapor, compress it, and then strategically recondense it back into the liquid stream being exported from the facility.
So they recycle it.
Exactly. Alternatively, this captured boil-off gas is rerouted to fuel the terminal's own internal power grid,
Oh, smart.
running its generators and vaporizers. The internal pressure must be perpetually analyzed and bled off to avert a structural rupture of the roof.
Which brings up a crucial logistical question posed by the engineering data. If you have a vessel holding a highly reactive, violently expanding cryogenic liquid, how do you safely extract it?
Carefully.
Right. You certainly don't just drill a hole and attach a valve to the bottom of the tank. In fact, our sources reveal a paramount safety feature here. There are absolutely no penetrations in the bottom or the sides of these tanks.
None whatsoever.
Every single pipe, pump, and access point is routed exclusively through the roof.
That is a non-negotiable tenet of cryogenic safety protocol. A bottom valve is a potential failure point under immense hydrostatic load.
Because all the weight is pressing down on it.
Exactly. To eliminate the risk of a catastrophic bottom drainage failure, the facility extracts the liquid vertically.